Believers were very out. To come about believers, for instance, what believers, we are waiting for Jesus. So, Jesus, our Savior.
Interrupts the class. So we and hopefully engineering surveying too. And now I away, and I'm sure everybody knows that and I get to the if you have a question at any point, you shall be attended to. So I'm going to share the screen. Maybe I should. Okay, are we all able to view the screen?
Yes.
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 Okay. Okay, so we shall proceed. Sonia, I have given you co-host rights. You should be able to admit people, so I don't have to check in the waiting room while class is going on. So kindly check the waiting room and admit people to the class. So through engineering, surveying 1, and I think I should put the video off for now. I will be taking you through engineering surveying 1, which is the course that you take in year 2, semester 1. So I a year 2 member. Is year 2 member. One. So engineering. Why do we have to study engineering surveying? You are studying to be engineers, and we do study or are practicing as surveyors. What is the connection between the engineers and the surveyors? When do we come in and what is expected? understanding of the principles of surveying. Suppose I am not sure at a level everybody should have level looks like. So when do we use the level on site? When do we, what kind of, how then do we use these measurements and of what you, and then it is also supposed to help us to have the hands-on feel of the surveying equipment. Sorry, I lost connection, but I think it is now restored. So I was saying your civil department shall handle the practical part, and the surveying department, we shall handle the theory part. And then the combination of two should help us to have a foundation or an understanding of what is expected of an engineer, what is expected of a surveyor, how they can work together to ensure that a construction or a civil engineering project is completed successfully. So by the end of this course, we should have a clear understanding of who does what between a surveyor, between an engineer. What kind of information does a surveyor hand over to an engineer? What kind of information does an engineer hand over to a surveyor? How do they work well together to be able to complete an assignment? And this is mainly construction of structure, including roads and also buildings. So that is the general background of this course. So I hope that is clear. Is that clear?
Yeah.
Is that clear? Do we proceed?
Yes.
Yes.
Okay. So then what is the learning outcomes? It is mainly what we have talked about, but now broken down into bullets. And learning outcome number one should be by the end of the course, every participant, learner or student should be able to identify basic surveying instruments that can be used on a construction site. Every student shall be able to. There's somebody's hand is up. Godfrey. Godfrey, have a question? Yes, please.
We are not seeing your screen.
Yes, Godfrey.
We are not seeing your screen. The screen sharing.
Is it everybody? Nobody is seeing the screen?
Yes.
No.
Yes.
Yes.
But initially we were seeing it.
Yeah.
Okay, let me reshare. Screen share. Okay, can we now see the screen?
Yes. Yeah.
Yes.
Okay, so now we can proceed to the learning outcomes. I say outcome number one or objective, the end product of an object, able to identify surveying equipment. We should be able to know which a laser scanner is, what a drone is. All that is the equipment that we actually. And then every student should be able to and carry out recognized to be used. I think this is not only engineering surveying professions, that before you
Oh, she has gone.
I think I am now back. Okay, I think I am back online. Kindly. Am I audible now?
Yes.
Okay, sorry for the interruption. I have changed position. Hope hopefully it will now be much better. Can we view the screen?
Yes.
Okay. So back to objectives. We said we should be able to identify different equipment we use. We should be able to carry out a reconnaissance to inform further processes, including budgeting, including preparation of methodology. Often on projects, when you're going to start, they ask for an inception report, which presents methodology and the other detail that you think you are going to implement, and that all happens after a reconnaissance. So this one cuts across, and it's very, very important for every project at any stage. We should be able to carry out basic surveying techniques. I have already talked about a level very many times. We use a level to measure height or reduced level or elevation. Every engineer should be able to easily prepare, perform leveling, and also compute and present results. We should be able to perform instrument checks to ensure they meet specifications. Along the way, we shall see how we perform checks on a leveling equipment or machine. You couldn't have done it before, I don't know, but if you haven't, we shall do it later on in the other topics. And this is to ensure that when we say we have a misclosure or an error of 5 millimeters or 5 centimeters, it is actually not because the machine has a problem. We need to be sure that the machine is okay before we embark on any exercise, be it leveling or use of GPS or using a drone, whatever equipment we have. to use. We should also be able to design and organize a survey, including estimation of probable errors. And this happens after a site visit. You will come back to office depending on your findings on site. Then you can adjust or modify or even maintain the methodology that you had earlier proposed. And then we should be able to produce drawings using standard software. And here we need to ensure compatibility. If a surveyor gives an engineer a drawing, will they be able to open it? If I am preparing a drawing and the end user is an engineer, then I should already know what software they use, so that if I have to prepare drawings for them, then I already predetermine the format that will be usable. Otherwise, you prepare very beautiful data, you transmit it, and nobody can actually use it. And then it has to be sent back and forth. So we should know the end user of our product. Construction project on a building, it can be a quantity surveyor, it can be an engineer, it can also be a surveyor, it can be a hydrologist, very many categories or branches of expertise. So when we prepare drawings, we need to mind the end user and cater for their interests and compatibility in terms of software. Then finally, we need to analyze, we need to report, and where appropriate, distribute the errors. We should be able to do an error analysis. If I ask you to get me levels of the main building section, let's say they are going to do the reconstruction, I need to know maybe the height or the elevation of floor 2 relative to floor 1, or floor 2 relative to the basement. And you tell me, well, I have done leveling from environment up to main building, and this is my elevation, and you give me your results, then my next question would be, what confidence do I have? What's the standard deviation? What quality tests did you take? If, for example, instead of while recording, you recorded 1.60 instead of 0.06, then how do I know that you transposed figures? What checks did you take? So that if I am taking the level and using it for further processes, then I should say I am confident I will have a standard deviation of maybe 5 millimeters of 10 centimeters, so that if it passes the test, then I can compile my report and submit the results. And one other thing that happens is you are still now a student, you're going to finish and go out to the field. Once you submit a report, you are fully accountable even after 30 years. So if you are endorsing any report, then it means you should be very, very sure that whatever you have reported is actually what happened. So that should be what we should have learned or understood by the time we finish this course. And like I said, it's a combination of the theory plus the practicals. So we should be able to balance the two. So if we don't have any questions, then we shall go to the next slide. If you have any question, you raise your hand. The main topics in this course, we have leveling, height measurements, we have distance measurement. I am sure we have all looked at a tape. We can measure distance, even a ruler. Let's start with something that is as basic as a ruler. And now, we have angle measurements. I am sure we all did mathematics, so we know what an angle means. So we shall see how do we measure angles, how do we measure distance, how do we measure height, and how do we combine these to be able to find position of a point, where position is ordinarily XY, but now we shall look at X, Y, and Z, where Z or H represents the height. So when we are mapping, we don't only do the 2D that we have always done, but we add the third component, which is the height, and which is the most important dimension of position or coordinates in construction projects. The nature of construction projects is we handle earthworks. For now, earthworks, you can refer to earthworks as volumes of materials. You have marram that you are bringing into site. You have stone base that you are bringing into site. You have asphalt that you are bringing into site. You also have waste material that you will excavate, not suitable, and take away from site. All these have a cost implication, both in terms of transport and the cost of the material. And all this can be computed based on height. So height is very, very important for any construction project, and it has a very big implication on cost. So again, I emphasize that when you prepare your report, you must do all the necessary checks. And once you have submitted, that should be it. Otherwise, then the design will keep changing. They will keep moving back and forth because of issues that you couldn't have sorted initially when you did the initial survey. And then we have coordinate systems. This will enable us to have the coordinates anyway. So if I say X, Y, Z, which coordinate system am I using? If I say latitude, longitude, and ellipsoidal height, which coordinate system? If I say northings, eastings, and height, which coordinate system? And when do I use what and where? One coordinate system may be used locally in your country. It may not be used elsewhere, even in a neighboring country. So we need to know which is what, and do I use which software. And then we'll have position fixing. We have mainly talked about position fixing. When you combine distance measurement, height measurement, and angle measurement, that is going to give you position, which is X, Y, Z. But how you combine those three is what determines what position fixing method you shall use. So that shall be our last topic. And in the last topic, we should be able to have simulated or even real observations and be able to get to positions, check their accuracy, check the state of the machine even before we do the observations, and then compile and present a report. That is our course content, and we shall be able to cover each and every detail of that. So I already said practicals will be handled by civil engineering department. So there you will consult whoever is in charge, so that when you report to university physically, then you are able to start on the practicals. Next. Okay, so like any other course, 60% goes to the exam, and myself, I contribute 20% through various ways. We are now having class. I'll be posting quizzes on Mwele. We shall have very many types of assessment. We could do a test. All that shall contribute 20%. And then the field work that is handled by the civil engineering department also takes 20%. So I have a few questions here. I have a few questions here which I will want us to answer together before we dive into the content of the introduction, which is our first topic. I am also sure we could have some people who have some already background knowledge in surveying or in civil engineering. They may help us answer the questions. And number one is, what do surveyors do? What do surveyors do? Is there anybody in the meeting?
Hello.
I see Rumba calling. Can you tell us what you think a surveyor does?
I think they can determine the topography of the area where the site is going to be constructed, something like that.
They can determine topography of an area.
Yeah.
And what is topography of what does topography mean in very simple terms?
That's like the slope of that. Is it steep? Is it like steepness and something else?
Okay. Thank you very much, Colin. And I think he has answered it. Surveyors can determine topography, and he's talking about how steep it is, how low it is, how high it is, and where it actually is. So the XY coordinate gives us the position, horizontal, and then the how steep, how low, how high will be given by the height. So surveyors take and analyze measurements, and he is very specific to topography or a topographic survey, which is something that we will talk about a lot, especially in engineering surveying too. And it is the foundation or the base information that engineers will use to do design. So we take and analyze measurements. But now which measurements you will take will depend on what project you are using. It could be different for a construction site, for a school. It could be different for a railway project, even the nature of the detail, even the density of the detail. So all that is dependent on what project you are actually doing. So we go to question 2. What do surveyors measure? This has also been answered already. Distance, angles, and position. So it is from the distances and angles and also elevations that we determine position. What distances do surveyors measure? Irumba maybe could help us answer this again. What distances do we measure?
Yeah.
Horizontal distances.
Horizontal distances. What else?
Vertical distances.
Vertical distances.
The vertical distance in terms of height.
Sorry?
Vertical distance is in form of height.
Okay, so I think that is Irumba's submission. And here we have horizontal distances, slope distances, and vertical distances. And now along the way, after we have covered the topic of distances in detail, then we should be able to move from one to the other. If I have measured a horizontal distance, what other measurements do I need to get back to the slope distance? And if I have measured the vertical, how do I get the slope or horizontal? We should be able to move from one to the other. We should also be able to know what other measurements we actually need. And because all of us did mathematics, we should be well versed with plane trigonometry. So we are able to combine the distances and angles to get us to where we want to be. What angles do surveyors measure? Here we have horizontal and vertical angles. Even when we use a theodolite, which is the basic angle measurement equipment, or ancient or traditional, we are able to measure angles in the horizontal plane and also in the vertical plane. So it means if I want the vertical distance or the elevation, then my vertical angle should be measured. And then I can use that together with other measurements to be able to compute measurements that I want. So what positions do surveyors measure? Here we have two. Position is position, X, Y, Z. So we have situations where we only want to be bothered with two-dimension position, which is what we are familiar with now, which is the X direction and the Y direction. And later on, we shall also see the difference between X, Y, then northings and eastings. And then we also have situations like the one Irumba talked about, where we need height. If I want to do a topographic survey of an area, I want to show the highest point, I want to show the lowest point. If it is a road, I want to show how much material is going to be cut at position A. I want to show how much is going to be filled at position B. Then I should be able to determine height. And it can be an absolute height, it can be a relative height. And the choice also of the datum that I use can be agreed upon, or it can be dictated in the terms of reference. And then lastly is who can perform surveys. Okay. So who can perform surveys? Here it really depends on for what purpose. Like I said earlier, a civil engineer should be able to do leveling. They should also be able to perform basic measurements on site. We should also know which measurements have to be taken by a surveyor, which measurements have to be taken by a QS. If it's a road probably and we need compensation for the affected pieces of land, then we shall have in a valuer. If we are doing drainage, then we will have a hydrologist. In some situations, we need a geologist. There are also people who pass as hydrogeologists, so they can do the drainage part as well as the soil part. So we need to know what measurements do we need, who is the end user, so we are able to know what exactly they need, and that shall inform our methodology of how we perform the task. So that was just so we have an insight into what surveying is. And then now we can get directly into our engineering surveying. So if there's any question, I'll attend to it. If there's none, then we can proceed. Okay. So this is a basic definition of surveying. Of course, I will not ask you to define surveying, but this is just so you know where we are coming from. So when we get into the core of the engineering bit, we can easily blend. Surveying will help us to determine position of points above or beneath the surface of the earth. Surveying will help us to define or to find position of points on the surface of the earth, above the surface of the earth, and also beneath the surface of the earth. And examples which we have already discussed include determining location, position, that's XY, determining elevation or height or reduced level, that is the Z, mapping location of utilities. For example, maybe we will have positions of transmission poles and the lines so they know which goes where. National water will have positions of their pipes, of their ducts. So we have electrical ducts, we have water, we have mechanical. For example, the cameras that have been installed, they can easily be located. So even when you are going to construct a road, you should already have this information. So you are not putting a road or cutting pipes here and there. It makes the process much easier. We should be able to find distance between 2 points. If I want to move from Kampala to Gulu, how long is it? If I want to fly from here to South Africa, how far is it? If I want to put control points for construction supervision, how far are they, and things like that. We should be able to determine position and length of boundary lines. This is now mainly land surveying, where we deal with survey of parcel boundaries or plot boundaries, so that neighbors, every person knows where their boundary line is, to minimize on the disputes, but also to produce a cadastral map that shows who has an interest where and how big is their interest or how small. And then determining areas of parcels of land. This also happens on construction projects. Once you have your road design, you have set it out. You need to know which parcels of land or plots of land are being affected for compensation purposes. So they need to be mapped out. You superimpose the design on them. So you know plot A is losing 10 decimals, plot 2 is losing an acre, and then you need to document that information for the valuers to be able to attach a value. And of course, this will not be done by a civil engineer, but the highest position on construction projects is normally an engineer who is the RIE, resident engineer. So even when you are not the expertise carrying out this, you should be informed of the process also to avoid loopholes. Otherwise, they will bring you a document you sign, and then at the end of the day, you are being answerable to things you did not even understand. And then we have determination of volumes of earthworks. This I already talked about. You need to quantify when you are billing on construction projects, you attach proof. So if you are saying we dumped 1 ton of maram, only levels can tell that you did. If you are saying we cleared bush clearing, 20-meter corridor, 10 left, 10 right, only measurements can actually tell that that happened. So all this information has to be well measured, recorded, and also presented. And then last, establishing points, lines, and levels needed for construction purposes on site. Now, a surveyor will prepare foundation data for the design. Like Irumba said, I may provide a topographic map for a road construction project for a building. Engineer will use the data and produce a design of a road, railway line, or building. And that comes back now to the surveyor to set out on ground. It is not mandatory, even when you are working on an existing road, that it maintains the horizontal alignment that it is. In areas where there are sharp curves, if you have room to reduce on the curve or to increase the radius, the smaller the radius, the bigger the curve, or the more inconveniencing it will be to maneuver through the curve. So you can have realignments. Where there are curves, you can realign, and then you find there are things you may not be able to move through. If like there's a graveyard, you cannot cut through, so you have to realign. And while realigning, you may actually create a curve. You may have a road that's going through a school. If you're going to tarmac it, it will definitely have to be realigned. So there are situations like that. So how do we know then where the actual designed road falls? That will be the duty of a surveyor. I give you the data, you design, you give me back the design, and I set out and show you where physically your new data or your design falls. If there is need for further adjustment, there is normally a realignment or a redesign. And on some projects, it happens at the same time. You pick data, they are designing, they are setting out and constructing. Those we call design and build projects. So you can clearly see that, first of all, a good design is dependent on what data the surveyor has provided. If for a low point in a valley, I am telling you there is a hill, clearly you're going to have messed up quantities. It means your drainage is going to be messed up and several other components of the design. So how good your design is as an engineer will be dependent on how good the data I have given you is. And then also it comes back to me when we are doing the setting out. And setting out is not only position XY, it is also in the height. So that when at the end of the day you say, I dumped 10 tons of maram, I will be able to compute my levels and indeed prove using figures that yes, this is what was deposited or dumped. So by now we should have a basic understanding of what surveying is, how we come into engineering surveying, what is expected of us, and it should be clear that an engineer and a surveyor will work hand in hand to have a successful project. Is that clear?
Yes.
If there's any question, we attend to it. If there's no question, we proceed. Okay. So what are the categories of surveying? I do not know if we all know what the shape of the earth looks like. Sonia, what is the shape of the earth?
It's spherical.
It is spherical. Spherical means a sphere. Or so we can go with what Sonia has said, that the earth is spherical, and whether it is purely spherical or not, we shall discuss later on in the course. But we now decide to assume that the earth is actually spherical, which is what we have learned anyway from the globe in geography. So it means if I have one point at the North Pole and I have another point at the South Pole, the line joining the 2 points is clearly not a flat line or a horizontal line from Sonia's definition or description of the earth. And this brings in the difference between plane surveying and geodetic surveying. Is if I am measuring a distance 100 meters apart, we can comfortably say it is a flat surface. and it passes without having to apply any corrections. But if I am measuring a distance from Uganda to South Africa, it is clearly not a flat surface. And therefore, if we are using assumptions that it is a horizontal surface, then we will clearly have problems. So if we are doing plane surveying, we are imagining or assuming that this is a small area, and therefore we can comfortably assume that we are working on a flat surface. And that is plane surveying, and there we apply plane trigonometry. When we are working with relatively long distances, and here it says 10 to 15 kilometers, but it can even be less than that, because if, for example, you have a road that stretches 100 kilometers, your errors or measurements are going to build up from 0 up to 100. So if you keep handling segments of 5 kilometers and assuming that you can assume that it is relatively flat, by the time you get to kilometer 100, you're definitely going to have issues. So for geodetic surveying, we use spherical trigonometry, which is just a modern version of plane trigonometry. And that means when we measure distances, we are not assuming they are horizontal. We need to apply a correction to the spherical distances to be able to have them horizontal. Because if we are representing this information in a CAD software, AutoCAD, Civil 3D, whatever it is that you use, we assume that XY is actually a plane surface. And then the height is perpendicular to this plane surface. So it should be clear when we are working with plane surveying, when we are working with geodetic surveying. And this is a very, very big problem for route projects, because if you assume that it is a flat surface, it could be, depending on where you are and how you are looking at the whole scope. But if you imagine you're at 0, the end is at 100, you definitely cannot pass with a plane surface or a horizontal surface. And we shall look into detail when we do position fixing, which is determining position using angles and distances. You realize that if you don't correct your distances for that curvature, your traverses or your position will never pass. And like I said, in engineering surveying, there is no room for making mistakes. If I submit wrong data to an engineer, they are going to design, and that design is going to be implemented. And the unfortunate bit is you may supply data today and construction happens 10 years later, when you don't even know what you did, you don't remember where the control points for reference were, and you will definitely have to redo it. And like I said, it affects the cost of the project. So if it's under budgeted simply because you supplied wrong data, then there's a whole lot to lose. So in engineering, we do right thing first time. There's no second opportunity. Second and third will be there, but will come with the heavy cost. So better you take your time, understand what you are supposed to do. If you don't have concepts clear, ask for guidance, do the right thing first time. So what is engineering surveying? What is engineering surveying? Can a volunteer help us define in basic terms what engineering surveying is?
Yes, madam.
Yes, Rachel.
Engineering surveying, it literally means the activities that we carry out to determine like the quantities or to get like enough data to help us in designing engineering work works like buildings, roads, bridges. Yes.
Thank you so much, Rachel. Rachel has summarized it all, what engineering surveying is. For an engineer on a construction site, engineering surveying is the process of measuring angles, distances, heights to help with the design, construction, supervision, and even after supervision, you have finished construction, you have handed over your site, there is a period where they have to do monitoring to ensure stability of your structure. It could be a building, it could be a bridge, it could be a road, whatever it is. So any surveying work involved or done or carried out on a construction site at any phase is what we refer to as engineering surveying. I hope that is clear, as basic as that. So when we pick X, Y, and supply to engineers to design, that is engineering surveying. They have designed, they are giving us data to physically position the structure on ground, that is surveying. We are taking levels to see if contractor has deposited 4 centimeters of asphalt, if they have deposited 100 millimeters of stone base, if they have deposited 150 millimeters of marram, all that is surveying. I hope that is very, very clear. This also involves the different methods of data acquisition, of processing, and presentation. Okay, I have muted Mohinda. So engineering surveying, here we say involves investigating land, using measurement tools, geographic knowledge to work out the best position to build bridges, to build tunnels, to build roads, or any other construction works. Like Irumba said, I may have a site that is 100 acres. I want to put a school. How do I know where I position it? There are very many things you have to think about. Where does the sun set? Where does the sun rise? Where does the stormwater go? How do we manage drainage? If it's a road, how many people is it going to affect? That's the social science bit. How many people are going to be displaced? Where are they going to be? Who is going to compensate them? Very many dimensions, both in science and in art, that we actually consider on a project, and all these will depend on the initial information a surveyor submits that represents the situation on ground. We should be able to produce plans. Here we can say data, topographic maps, or whatever form of information is needed that will facilitate the design. We should be able to set out on site. This we have said time and again. If I have a design, how do I put it on ground to the right place? We have talked about as monitoring and as built. Normally, if there is a design for a project after you have completed with construction, then we must audit and be able to see if you are required to have a carriageway width of 7 meters. Is it 7 meters? If you are required to have type A drainage, is it type A drainage? If you are required to have 8 centimeters of asphalt, is it what is there? Even things as simple as signages. If you are supposed to put a signage here for a bridge, a signage for a hump was placed there. So all these fall under as built. So an as built survey is more like a topographic survey that you initially submit for design, but now it is actually more detailed because you have to capture each and every element. So it is compared against the design, and then you can comfortably say, yes, the contractor fulfilled their obligation or they did not. And then we have deformation monitoring, providing control points, often for big structures, dams, bridges, even roads that may have high traffic or high elements of fill. You may actually need to consider monitoring their stability, both in X and Y. We can have cracks that are horizontal. We can also have failures that are vertical. So when you're monitoring, you do both X, Y, and Z. You have seen buildings collapse. You have entered into a building and you see elements of failure. There's a column which is broken horizontal, and of course, engineers are experts, so that bit of stress and strain, you should be able to manage very well. So you know when there is danger, so you can alarm, and you know when the situation can be contained. So that is engineering surveying. And if there is no question, then we will look at other types of surveying. This is simply so you know, like we said, on a construction project, you will have an engineer, and engineer can be a highway engineer, they can be a hydrologist. You will have a geologist, the soil engineer, an expert in the soil who will test the materials and whatever it is. You will have a surveyor. If it's a building, you'll have mechanical and electrical. On all projects, you have environmental impact assessment. So you have a series of experts on every project, and therefore you should know who does what. Also, it creates clear line of communication. So if I know that, if I want data for drainage, I will ask the hydrologist. If it's a building, I want to know the reduced levels maybe of the ducts for electrical and mechanical, then I know who to ask. So it is very clear you understand the nature of the project, which parties are there and how well to work with them. Unfortunately, in engineering surveying, you cannot work independently. If you are put to major elsewhere in engineering surveying, somebody's input helps things to move in several other ways. So you must, graphic surveying, this deals with surveys to water. We have photogrammetry. I am sure we have all seen drones at parties. We have all read about drones and UAVs. We fly, we take photos, and then we can generate information from these photos. And it will not be as good as when we take out a level and a total station and a GPS, but if you want a rapid kind of output, then it can work very well. And then we have remote sensing. Remote sensing and photogrammetry are more or less the same, only that photogrammetry, we have a camera up there. It can be on an aircraft, it can be on an unmanned aircraft, which is a drone. And for remote sensing, the cameras are installed on satellites. So you have a satellite there taking images, relaying them to the center, and then you can access them. And we actually have satellite images that are also as good as 5 centimeters, 5 centimeter resolution. Of course, they will be expensive, but if you cannot fly a drone, which is closer and better resolution, then it can be the next alternative. So actually, photogrammetry and remote sensing can be used in engineering surveys for preliminary design. If I have a road, I want it to move from point A to point B, I can already use images. Even Google Earth is part of this repository of images. I can use it to do the preliminary design. And at a later stage, then I would do the traditional data capture to be able to submit sufficient data for the detailed design. And then we have GIS. This is simply a way of merging spatial data. Spatial data is coordinates. So it is a way of merging coordinates to the non-spatial data. We have, for example, talked about if we are building a road, we need to compensate the owners of the parcels that are affected. So the surveyor will capture the coordinates of these parcels so we know the extents and the coverage. And then these plots have owners. So we probably have to know who is the owner by name. Where does the owner live? Is the owner married or not? Because when you're doing compensation, then you don't want to pay the man and later on the woman says the property is mine and therefore I need compensation. You need to know what kind of proof of ownership they have. You may compensate somebody with an agreement and then somebody with a title comes up later. And this happens a lot in central part because of this tenant landlord kind of situation. Is the people on ground are not the landlords. They have the agreements, but they do not have the titles. So all this information will be attached to this map or to these coordinates. So I know plot A is affected. It is affected by, we need to buy off maybe 10 decimals. And it belongs to Diana. Diana is married. She has 10 dependents. And the LC has to acknowledge that, yes, this is the right information. Kindly go ahead and give them 200 million. So this GIS system will help us to consolidate that information so that we have a proper archive. Cartography, this is simply map making. We have cadastral surveys, is mapping of plots in a layman's language, mapping of plots or parcels of land. And then we have the topographic surveying that Irumba talked about. Topographic surveying, we do this all the time in engineering surveying. Success of any project will depend on how good your topographic survey was. It involves collecting data, preparing maps, showing locations of natural and man-made features and elevations of points on the ground for multiple uses. So if you're going to design, all you require from the surveyor is X, Y, Z of points within your project area. If it's a road, your corridor. If it's a railway line, your corridor. You need a very accurate and well-spaced distribution of your X, Y, and Z. And it is purely onto that X, Y, and Z that you will do the design. That is the geometric design. We should also know which is what. We have the drainage, we have geometric. This you can download from the website of Ministry of Works. Pavement design, so you know where you fall. Am I a highway person, or do I want to eventually be a highway design person? Do I want to be a bridge person? Do I want to do drainage? So then it dictates where one falls. But of course, at this level, you should have a general understanding of all those, and then you can specialize later on. But the supply of the information will also depend. What purpose do I need this data? Is it a road? Is it a building? Is it a bridge? And what kind of information do I need? And remember, when you are hired on a project, you are an expert. And therefore, any mistakes in the instructions or in the terms of reference are not going to be blamed on the client. They will be blamed on you, the expert. So if you realize there's a gap somewhere, you should already raise it or address it even prior to start of the project. So those are the other types of surveying that we may encounter along the way. For example, in engineering surveying, we have topo, we have cadastral, we have hydrographic. We may actually also do photogrammetry and remote sensing if we use Google Earth to do preliminary design. And then we definitely have the GIS because everybody has to manage their information somehow using different software. Then we have route surveys, which is topographic survey of a corridor. So route survey is under topographic surveying. I could do topographic surveying of a site for construction of a school, a mall, whatever it is. So if I am surveying a corridor for a route, it can be a railway, it can be a pipeline. We talked about umeme, transmission lines. All that is categorized under route surveying. And those are the types of surveying. Not actually all, those are some of the types of surveying. So if there is no question, then we can look at the different equipment that we use to facilitate this work. Okay, no question. We have a theodolite. I see Ampumuza's hand up. You can put your question through.
Actually, as you are talking about,
And ask.
hello, as you are actually talking about,
Yes, I can hear you.
as we are talking about the activities encountered in engineering surveying, there is some term that you use control points, and we don't understand that.
Yes, which term was that?
Control point.
Okay, a control point. Let me just let me stop sharing and I see if I can get a photo of a control point here. So okay, so I go back here. Screen share again. Share. Can we all view the screen?
Yes.
So what we see there in those three photos is what we refer to as a control point. And it is simply a point whose coordinates we know. So I have control point DSL 01. I know it's X, I know it's Y coordinate, I know it's Z coordinate. And there are types also of construction or monumentation of these control points. This is an iron pin cast in concrete. You can have a mast, like Naguru, there's a mast, Naguru Hill, there's a mast at Korolo Hill whose coordinates we know. Those are also control points, and we use them in several ways. For example, this that I have displayed here, I can set up my machine on it. If I scroll down, you will see here, this is a GPS instrument set up at a control point. If it is leveling, I will carry my leveling rod or staff onto that point, onto the nail, and take my measurements. And then it can also be a point that has a GPS like this, full time, it is recording and sending information to a computer somewhere in an office, the control center, and then we can be able to access that information. So in very simple words, a control point is a point whose coordinates we know. and it is a basis of controlling our surveying or topographic surveying or data collection. Is I place my machine on a known point, or I place my machine somewhere and read onto a known point, so I am able to attach coordinates to my newly collected data. Is that clear? I hope that is clear. I will stop
yeah.
sharing.
Thank you.
Okay, then there is a hand from Cassidia Henry. Cassidia Henry, can you please ask?
Yes, I have a question.
Yes, please.
You are saying that I have to make sure that the report which I'm endorsing is true and correct, and yet I'm receiving this data from a surveyor who did this survey when I'm not even on ground. So to what extent am I really responsible?
Yes, Henry. If I am the surveyor and Henry is an engineer on the project, I will prepare a survey report, which I will fully endorse before I submit. So I have committed that I have given you true and correct data. You have received it as an engineer. You are not going to endorse my report and say what they have given me is true, but you are going to utilize my information to prepare your design. And before you submit your design for further processes, you shall also commit to having prepared the correct design. So I have my survey report signed off. You have your design report plus all the design detail, the drawings, the plan and profile drawings. And then you shall also sign off and submit it to the next steps that happened in the design, not as a result of poor data, you shall be responsible. If there is a mess in the design as a result of mistakes in my topo data, then it shall be my responsibility. Is that clear?
Okay, thank you. Yes, thank you.
Yes.
But the assumption is also you have been hired, Henry, as an expert. So there are also some errors that you should detect. If at all they pass the surveyor, you will not be responsible. Everybody somehow is for your input and not the other person's input.
Okay, madam, thank you so much.
Oh, okay. Any other question? Okay, Henry's hand is still up. Okay. So now we talk about equipment use to measure distance, rather to take measurements in surveying that we use also on construction sites. There's a transit or theodolite. I don't know if anybody has seen how a theodolite looks like. A theodolite is used to measure angles. It can be in the horizontal direction. It can be in the vertical direction. Then we have a level, which is what I think by now, as an engineer, you should have already seen or used, or at least you should know what it is. And we use this to measure height or elevation or reduced level. Then we have a tape to measure distance. Then we have what we refer to as an EDM electronic not electronic distance measurement devices. And they are of several sorts. You have some embedded on machines. You can have a small equipment that sends in a laser and back. But the whole difference between tape and EDM is that for EDM, it's digital. You read off the screen, and then for a tape, it's manual. You stretch and read. Then we have a total station. Total station is a combination of a theodolite and an EDM. So a theodolite ordinarily measures angles. And we can have an electronic theodolite or one where you have to measure, to look through the telescope and read off the angles. So if we have a theodolite that's embedded with a distance measuring device, then that becomes a total station. And then we have GNSS, which we refer to as GPS most of the time. GPS is Global Positioning System. GNSS is Global Navigation Satellite System. So GNSS is the broader picture. It's all satellite measuring or measurement systems are embedded into that. And GPS is the GNSS of America. GLONASS is the GNSS of Russia. Beidou is the GNSS of China. Galileo is the GNSS of Europe. So maybe we shall have one for Uganda, hopefully soon. So the general picture is GNSS, and then these smaller ones are dependent on who innovated, who mans it. So you'll find GPS is completely in the hands of the Americans. However, we can get data free of charge. To levy a cost on it, then that will also happen. Then we have the 3D laser scanner. This is also a technology that is now growing very fast, especially in works where we have to work with volumes of earthworks to compute volume, stockpiles. If you have a heap of stone base, you have a heap of whatever material it is, you scan. And what we have out of this laser scanning data is simply X, Y, Z, but the densification of the data is much more than the traditional methods. So it sweeps, it has a camera that takes a photograph. It also takes the X, Y, and Z. So you can generate a model out of this. If, for example, you want to have a building, to scan an existing building, you can use a laser scanner. It will give you proper representation 3D of the way it actually is. You can then measure off the sizes of the different components, the windows, the heights of the floors, and things like that. Problem is it generates a lot of data. So you have to have a high-speed machine or computer to be able to utilize the information, and also the time to be able to decode your information. So we have pictures there of some of the machines we have talked about. To the top left, we have a tape. It doesn't have to be a steel tape, some are fiber, and that is used to measure distance. Then you have a theodolite, bottom left. This is an electronic theodolite because you see it has a screen where you can read off your angles. If it were a theodolite that's not electronic, then you would not have that window. You simply look through the telescope, you read the horizontal and vertical circles. Then top right, we have a total station. We said this is a theodolite merged with a distance, electronic distance measuring device. So a theodolite can only measure angles. A total station can measure both angles and distances. And at the bottom here is an EDM, but we said it can be in several other presentations. Then to the top left here, we have a transit, an older version of the theodolite. It's also for measuring angles. Probably even in the university, we don't have this now. It's an old technology. Then to the bottom left is a GPS. Also the pictures I displayed when somebody asked about control points was also GPS machines installed on some points. To the top right, which I believe should be your favorite, a long ruler. A level is only used to measure height. Only used to measure height. No angles, no distances. Bottom left, we have a handheld GPS. This is a version of GPS that gives you coordinates in real time. But this is simply for maybe navigation, recreation purposes. We do not use it for surveying works or for geodetic surveying. Then we have a digital level, left top, very beautiful machine. The level that we saw here with the rod is an analog one. So you look through the telescope and read off the ruler. This digital one here, you target, make sure the level is at the center, make sure the level of the rod is at the center. You press a button, it reads, it displays the height on the screen. It also has an option where you can automatically record, but you can also note down your measurements in a book. Then bottom left is the laser scanner. This laser scanner is like a total station embedded with the camera. So it sweeps out, records X, Y, Z, also takes a photo. So that when you're doing reconstruction, what was white in the building, it can attach color to the points. So you know this is a roof, this is a window, this is a gutter, and things like that. This laser depending on the use of your data, then if it's the best option that you can have, then you can go for it. For example, you want to reconstruct the building, we have fire, it's burnt and it's normal. If you had done a laser scanner of the building before, then you can use that model to be able to reconstruct and know what was where, the layout of the floors. You can use it both outdoor and also indoor. Then to the top right, we have a Lydia survey. Here we have a camera on an aircraft. Similar technology with the laser scanner, only that now this is just above. Laser scanner is on the surface of the earth, but it's the same. It sweeps out, picks X, Y, Z, also takes photos, so you can attach real colors to your points. And then to the bottom left, we have data collectors. These are also part of the GNSS system, which we shall discuss later on in detail. Then we have a ranging rod. We have a surveyor's nail. It's good when you're going to the field to have some nails in your box somewhere. And then we have a plumbing bob. This one, when you use a theodolite or a total station, you actually, even GPS, you may need this to center. The control points that I displayed, you recognize that it has an iron pin at the center of the concrete. So when you're setting up the machine, you set it directly above the nail. Sorry for the interruption. I was talking about this plumb bob. When we set up a machine, we set it directly above that nail. So you hang this plumb bob, it has a string, you tie it under the tripod. I don't know if everybody knows what a tripod looks like, but it's that three-legged gadget where we set up the machine. It can be a level, it can be a total station, it can be a theodolite, it can be a GPS. So it has a hook just beneath. So that's where you tie the string and then the plumb bob is hanging. And once it is stable, it should rest just above that nail. So that is what we use to do the centering. But modern machines have a laser beam, which you just press and then it drops the beam at the control point, and then you can move the tripod back and forth to ensure the laser beam is just at the nail. Others also have an optical plummet. Optical plummet is like a small telescope beneath which you look through, and then you can see if your machine is directly above the nail or not. So when we center, we level, we make sure the machine is well leveled, it is also well centered or prepared above the nail. Otherwise, if I am assuming that coordinates of the nail is X, Y, Z, and then I have set it aside, it means already my coordinates that I pick are going to be biased by that element. So that is, I think, some of the equipment that I managed to put here. There are several others. Like I said, there's a drone UAV, which will do the same as a LiDAR survey, but now this is a manned aircraft. So you can try to read and find out the other equipment that you will actually use. And then there are some you actually also already use as engineers. We have used a vernier caliper before. I am sure you remember what a vernier caliper is, to monitor cracks on roads. If they are really small, you want to measure over time and see if it's expanding, if it's stable or otherwise. So it really depends on the cause of your measurement. It depends on the accuracy required. It depends on basically, generally, the terms of reference of your assignment that will decide which machine to use. If you're required 5mm accuracy, then you get a machine that will help you get that. If you require a meter, then you can even use the handheld GPS. And then you can't use a tape and you claim that you measured to sub-millimeter accuracy, because the smallest partition, I think, is 1 millimeter. So how accurate your data will be will also depend on what machine you have used and also the procedures you have taken and things like that. So if that is okay, then we shall, which I think is almost the last 2 or 3 slides, is how are engineering surveys conducted? And this we have talked about in the 1 or so hours that we have been discussing. So this is just to put things in order so we know what falls where. Number 1, let's say you have a road project that you are required to work on. Visit the site. This will help you to do the necessary preparations. Maybe you thought you could use GPS, but it is a forest and you cannot be able to work with canopy. Then use a total station. This helps you to prepare generally, but also to budget for your field work. Maybe when you submitted the financial proposal, you assumed that you will spend 100 million. When you do reconnaissance, you can tone it down to maybe 50 or to 200. So reconnaissance is a must for every task, however simple it appears. Then we have field work and data collection. This we have also discussed in one way or another. Then we have computing and data processing. We will assume for our road project that the data collection is a topographic survey. Then we have submitted it to the design office. Design office has done the geometric design. They have prepared the maps or plans. We call them plan and profile drawings, where plan is the XY, and then profile is the vertical. So when we do geometric design, we do the horizontal alignment and vertical alignment. And all this is presented both in data format, but also in drawings. So an engineer or the design team will provide now the full design, normally in books, very well prepared. Now it is the task of a surveyor to be able to set out or stake out, and this is setting out the project physically on ground. So I say the center line is here, road edge is here, road edge is here, the shoulder is here, the drainage is here, and things like that, both in XY, which is horizontal, and also in the height. So I will be able to know that there is a fill here of 1 meter, there is a cut here of ½ a meter. And then the detail of what material goes where, now that is for the geotechnical team. And so that's the surveying process majorly. We have set out on ground, and then there is supervision. Well, staking out is part of supervision. When construction is happening, there is a contractor on site. There is also a consultant on site. The contractor does the work, the consultant does the supervision. So contractor will tell me, for example, I have set out the center line of the road from kilometer 0 to kilometer 10. If I am the consultant, I will then take my total station, go to site. I ask them to show me which points they have set out. I will confirm that those are the points. Once I have confirmed there is that form they will have sent me to cause me to go and check, I shall sign and say yes, the points are set out correctly. I shall append the coordinates of those points to that form, and then I shall endorse and submit. After I have endorsed, if tomorrow we realize that the center line set out was the wrong center line, then I am responsible. So when you get onto a construction site, if you are a Christian, the way you read the Bible is the way you should read the design drawings and whatever information is related to that. Every reference shall be made to the drawings. Otherwise, contractor can decide to alter, they can realign, maybe they've reached somewhere, they realize there's a rock and there is no budget for rock. And then what they will do, they don't inform you, they just make a small realignment, which you may not physically actually notice. And then you come for you check with the coordinates they have provided you, you read and things are okay, you sign. When you later on go to the design drawing, you realize that it's not what you were supposed to set out. So you must follow the design. If you have to change anything against the design, it has to be agreed upon. And it should be in writing. I am getting an echo, I don't know why. Okay, maybe it is now okay. So that is the process for surveying. Some of the processes may cut across with the processes, but this is specifically for engineering surveying because of the nature is that we pick data, we give it to the design team gives us the design, we set out, we monitor, we supervise, and then we do the as-built survey, and then finally we do the monitoring to ensure that whatever we have made is actually stable. Okay, so that is the surveying process. This one talks about horizontal and vertical control. We shall, however, talk about this in detail. And when somebody asks what a control point is, we already said, we'll say it again, that how good your data is will also depend on how good your control points are. We, however, have national control points which have been established and they have passed the standards, and these we get from Ministry of Lands, Housing and Urban in Entebbe under the surveying department. So if I am going to work in an area, I will rush to Entebbe and ask them for the control points that have been approved and have been published as national control, and I will look out for those to be able to read onto the ones that I have established. But like I said, this we shall discuss later on to detail. And then just a slide or two about errors. One thing we must appreciate in surveying is that when you measure your measurements are never free. Check your machine and whatever it is, error. So then the next thing would be, and if it is not free of error, then what do I do? So we have three basic types of errors. We have systematic, and I'll give very basic examples to help us understand easily. A systematic error, let's take an example of a measuring tape. My measuring tape is supposed to run from 0, let's say, to 30 meters. But when the manufacturer was making this tape, instead of making it 30 meters, it is actually 28. But the labeling on it goes up to 30 meters. And this may be distributed across so that you get the 2 meter difference divided by 30 and know that in every meter you lose this much. But it can also be maybe 2 meters missing. Another example would be you are using a tape It runs from 0 to 30, but maybe instead of starting at 0, you lost maybe 5 centimeters off the 0 up to 5 centimeters. When you're doing measurements, you don't realize that you actually, your tape instead of beginning at 0, it begins at 5 centimeters. And this is going to be carried on to all your measurements. The beauty with this kind of error is that when you realize, then you will sit back in office. If there was a 5 centimeter portion missing, then it means whatever distance you measured, you can subtract the 5 centimeters. And then you will be up to what is required. If you realize that a tape, instead of being 30, it was 28, and you can compute the effect of that depending on how it is distributed, then you can apply that correction to your measurements. The other example I can give that was for distance for angles. When we are measuring angles, angles increase in clockwise direction. But a total station can be set to have its increment in the other way round. So it means if I set at 0 and I rotate clockwise 90 degrees, it is going to give me 360 minus 90. If you're using 270 to make your computations, then you may not get to what you want. But if you sit down and figure out that your angle increment direction was actually twisted, then you can subtract the 360 from all your measurements, and then you will get to the correct measurements. So systematic errors can easily be designed and corrected. We have gross errors. These are simply mistakes or blunders. I am observing, and because I am chatting with somebody or I am on phone or something, I am distracted. Instead of recording 1.72, I have recorded 1.27. Very, very careless mistakes, which you can avoid if you are very organized. If I am measuring a distance of 100 meters, I have a tape of 30 meters, it means I will do full tape length 3 times and then a portion. At the end, instead of recording 3 full tapes plus the portion, I do 2 full tapes plus the portion. The only thing we can do for gross errors is to try to avoid them. Otherwise, if you have recorded 1.72, instead of 1.27, there is no way you will sit down and actually figure out that while at point A, I transpose the figures. So this you can only take care while you are doing measurements. Normally when we are doing leveling, you read out the height 3 times. If I am on the machine you are writing, I will say 1.702, 1.702, 1.702, just to confirm. And then we have random errors. This cannot, you really cannot attach it to any cause. The beauty is that they have the normal distribution. I am sure we have done statistics since we are of mathematics background. So these random errors are treated using statistical approaches or probability models. Standard deviation that tests several tests to give the confidence level and things like that. But to deal with, first is a systematic, remove systematic. If there are no gross, then the rest you can use the statistical methods to be able to solve them. This is the last slide, so people should not worry. This is just a few terms related to errors and accuracy. Accuracy is the measure between the relationship between the measured value and the true value. Like we have said in surveying, we do not have true measurements. So you know that you may predict the true value, the measured value will never be equal to the true value. The difference between the two is what is referred to as accuracy. So if your desire is to measure 10 meters, you have measured 11, your accuracy is completely poor, but also depending on what gadget you are using. If you're using a tape, may be bearable. If you are using an EDM, then you definitely have to have sub-millimeter accuracy. Then precision is a degree of closeness. If I have measured a distance 10 times, what is the relationship between the 10 measurements? If I have 1 meter, then 2 meters, then 1 meter, then 4 meters, there's definitely a problem. How do they relate? How close are they? Then if you have 10, the rest are 1 meter point something, then there's one that is 2. You can clearly tell that that is a gross error and you remove it. And that's why in surveying, we are advised to take redundant measurements, even when we are doing angles, even when we are doing distance, so that when there is a problem, you have a starting point. And uncertainty is the range within which it is expected the error of a measurement will fall. We all know standard deviation. So if you have computed coordinates of a control point and you tell me the height is 1200, you should tell me, but you should use it to this accuracy, maybe plus or minus 2 centimeters, plus or minus 2 millimeters. So that if my desire is to achieve 1 millimeter and your point is already at 5 millimeters, then I should do otherwise. It means I will not be able to use it. And that is the end of our presentation. So if there are any questions, I will attend to them. And if there are no questions, I shall talk about Muele platform a bit. I shared with Sonia the code, but I can see that almost nobody has enrolled, apart from the 2 people that I enrolled. So I would like to know if we have been, that is if there is no question, if we have been given the enrollment code for the course. All that I have discussed today is already there, plus 2 or 3 topics ahead. Somebody with a question?
Yes.
Henry's hand up.
Question, please.
Yes, I can hear.
Yes, are you hearing me?
Yes, I can.
You talked of decimals. There's a statement you made which included 10 decimals. Can you say something about the way these decimals are determined, please, shortly?
Okay. This is Henry. Henry, decimals is a way of representing area. So we can have hectares, we can have acres, then we can have decimals. And of course, you have the square kilometers, the square meters. I can give briefly how they relate, but you'll probably have to do some more research, note them somewhere, but with time, they will be part of you. A hectare has 2.471 acres, and 10,000 square meters is equal to 1 hectare. 10,000 square meters is equal to 1 hectare. 1 hectare is equal to 2.471 acres. An acre has 100 decimals. And these decimals we normally use in mapping plots in cadastral surveys. You normally hear people say 100 by 50, 100 by 50. 100 by 50 is actually feet and not meters. But if you compute from feet to meters, then to acres or to decimals, a 50 by 100 shall amount to 11 point something, between 11 and 12 decimals. So when we are doing construction of roads and we are doing values for compensation of the affected parcels, that is when the decimals come in to represent the area. It is a unit that we are accustomed to for measuring area. Like I said, you can do square meters, even square kilometers, even square miles, depending on how big the parcel is. You can do hectares, you can do acres, you can do decimals. And then you should also be able to relate easily feet with meters. 1 foot is 0.3048 meters. So Henry, if you're in the field and you're walking around, client asks you estimate for me the area of this parcel, you should be able to do that easily. You're not going to say you're not a surveyor. All you need to know is have those parameters off head, and you should be able to easily run from one to the other. Have I answered your question, Henry?
Yes, you've answered me. Thank you so much.
Any other question?
Yes, I have a question, madam.
Yes, Martin.
Yeah, is it possible to generate a topography report of an area of like 120 by 540, but I'm using like only GPS coordinates?
You are going to repeat your question slowly.
Is it possible to generate a complete topography report while I'm using coordinates, GPS coordinates? That's like probably latitudes and longitudes of like some control points, I think could be on the site. Is it possible to do it?
You mentioned some dimensions which you have not mentioned now.
Oh yeah, like for the area of the place, it's 120 feet by 540 feet, 540 feet. Yeah, so if I want to generate a topography report of that area using GPS coordinates, is it possible to be done?
And what do you mean by using GPS coordinates?
Yeah, I want, okay, in some part, for a specific area of the land, it's a bit slopy, and then there is some other place that's a bit horizontal. So if I want to generate a topography report of that place, I clearly don't have theodolites and levels and all that stuff. But I want to do the report. So
I understand your question now.
Yeah.
Now, one thing, maybe too many technical things may not make sense now, but when we are attaching coordinates to control points, for X and Y, you can use GPS, you can use a theodolite, you can use a total station.
Yeah.
For Z, you must use a level. That is if you have built your control point and you want to assign coordinates to it. X, Y, you can use GPS, that is in static. You can use theodolite, you can use a total station. For height, you must level. Now, after you have done whatever you did for horizontal and you have used a level to extend your height to your control point, now you can place your GPS on that control point and do the detailed survey that you are talking about in what we call real-time kinematic mode. Real-time kinematic mode. So for the detailed topo survey, yes, you can use GPS to pick X, Y, Z. But for establishing control points for height, you must level. And I hope that is very, very clear. We don't use GPS to establish heights of control points. But once your control point is on site or your control points are on site, then you can use GPS or even total station to pick the detail, which is X, Y, and Z. Martin, I hope I have answered your question.
Yes, thank you.
You're welcome.
Oh, another thing. So,
yes.
So in other words, I can't really do without a level. If I'm going to perform like some steps, I really have to get the level.
Martin, in construction, you must, and it is a must in bold and capital letters, use a level for height. If we are checking if a contractor says I have put 10 centimeters of maram on a road, we should have taken levels before they dumped and compacted. We again take levels after they have dumped and compacted. And at the center line, road edge, then we subtract these levels to actually see that it is 10 centimeters. Now, if you are working with GPS, its height could even be off by 5 centimeters or even worse in bad condition. So it means you can actually say they did not dump when they actually dumped. So to monitor levels, you must use a level, no shortcut. You can use station and GPS to do the detailed topographic survey for design. After design has happened, for supervision, for monitoring, you have to use a level to monitor levels.
Okay, thank you.
Thank you too. Any other question?
Yes, I was wondering how they do underground surveys, like those performed at Karuma Dam or sewers.
Elizabeth wants to do underground surveys. We also have methods that we use in underground surveying. There's also specialized equipment that you use for underground surveying. But for tunnels, then you have to be able to move through. Of course, the environment is quite nasty. There is no light and things like that. But like I said, there's specialized equipment. When there's a tunnel, you have to find control point somewhere outside, and then you take it in. You will either find other controls on the other exit, or you can manage with the set of control points that you have. Either way, it has to be controlled or tied to a certain network of control points. So you must still be able to physically access. And that is mainly under mining surveying. It's where we do a lot of tunneling surveys. So specialized equipment, but you have to tie your survey to a control point somewhere. And in this case, it has to be out. So you have your survey initialized at the surface, and then you dip into your tunnel, do whatever you have to do there. You can come back and close, or you can exit and close at another point. Elizabeth, does that answer your question?
Yes, yes, it does. Thank you.
Thank you too. Any other question?
Yes, madam.
Yes, Mark.
I would like to know, how do I get a specific height for my control point? Because I understand when I use a level, each time I change the position of the instrument, I'm going to get a different relative height for that control point. So which specific height do I assign to my control point?
Mark, we have several ways of doing that. The best would be find an existing control that already has a height assigned to it. I said before that we have national control points, and these are both for XY, horizontal, and also for the vertical. The traditional height benchmarks were put onto buildings. So you have a plate on a building, it has a line, and they will indicate that the reduced level of this line is say 1200. So let's say I want to have heights at main building. Well, fortunately at main building, there's a height benchmark on the wall at the basement, but there is another at environment. So what happens is you take your level to environment close to your benchmark, put your stuff. I can see you are familiar with the measurements, backside, interside, and things like that. Open with your backside with the level at your control point on the wall. Like I said, the traditional ones are on the wall, but there are some that are also attached onto these, the monumented ones, like the one I displayed, where you have a pin and you have established the height of that pin. Then you do a series of backsides, intersides, backsides, intersides, until you get to your site or to your point that you have established, whose height you need to establish. Now, the best practice is open at a known point. That means take a backside at the known point. You do a series of backsides, foresides until you get to your point. Close back at a known point. So let's say I open at environment, I read, let's say my point is at agriculture, I read onto that point, I proceed and read the last foresight at the control point at main building. So it means I know the height of environment, I know the height of main building. So when I compute my levels until main building, if the computed level of main building is close to what I know, it means I am okay. If it is not, it means there is a problem. Like we talked about, you can transpose a figure. When you're stretching that road, you may, instead of pulling out 1-2 meters, you may leave one stack under, so that from 1, you instead go to 2, then you miss 3, the next is 4. Very many things can happen. So that's why it's very important that you do your backside at a known point, you do your final foresight at a known point. When you compute the levels, you hold, of course, one, compute the other. If it is reasonable within your allowable misclosure, you proceed and adjust. If it is not, then you have to redo. Now, in situations where, for example, you have a stretch of 100 kilometers, your control point is at 0. I'll give an example of a road that I have worked on before. From Kitgum to Atiak, there is height benchmarks, 2 of them in Kitgum. There is none along the way until Atiak. So what would mean is you level from Kitgum to Atiak, then back to Kitgum, which is clearly not practical. If you carry on errors from 0 to 60 kilometers and back, then clearly you're going to be off by the time you go back. So what happens is you moderate your leveling network. If you have 60 kilometers, you're going to build control points every maximum 300 meters. Ideal would be 200 meters. So every 200 to 300 meters, you have one control point. So what happens is you run from the national benchmark to your first point at kilometer 0 and run back and close. Actually, Kitgum has two, so we're able to run from one, read over the first point and close at the other. If it is okay, you compute. Then now what happens after that? You run from 0 to 200 meters and close back. So you run from point A to point B, compute the change in height between the two, then run from point B back to point 1, again compute the change in height. So you'll have the change in height for the first leg, you have the change in height for the second leg. Compare the two. If they are beyond 5 millimeters, you terminate and read again. If they are 5 millimeters and better, then you now move from point B to C. Then again, C back to B, and you compute again. That is what we refer to as differential leveling. Mark, have I answered your question?
Yes, you have answered. Thank you, madam.
Okay. I think Mark already has some background knowledge in leveling, so the rest don't have to worry. All this that we have talked about, we shall learn in detail in the height measurement topic. Any other question? Okay, so now we go back to Mwele. Like I said, I shared the code with Sonia, and I can, if you can see my screen, only Sonia and Raymond are enrolled, and it is myself who enrolled them. So I don't know if Sonia did not share the code. Is Sonia still on? Sonia, are you there? Can you tell us if you shared the code or not, and why you did not?
She actually shared the code. I think you just have to refresh that page.
Oh, I have just signed in. So have enrolled 2103. I have, okay, I have posted to, let me share the code here so everybody can pick it. That is the code enrollment code CIV2103. So as you may see, the course is up and running. And if you go to the page, there's everything you need. Whenever there's an announcement, I will post it in the announcement section. I think there's something there, but we have not seen it, start of classes. And there's a welcome message, well, that you may read or not. There's resource and tools section. This is where I post whatever information you need. There's a timetable there. There's a good book on coordinate systems, which we may need later on. But now the core is the topics. So we have introduction to surveying, which we have done today. And when we go there, we can download the PowerPoint presentation. We can download the notes. There's a Word document. When you click here, then you have all the detail, the learning outcomes, the subtopics for each and every topic. So we have finished introduction to surveying. I will secure some time and post a quiz under that topic. And that is already part of assessment. So those who have not enrolled should enroll. And when I post a quiz, it is not open-ended. It will be for a particular time. So you need to be checking very often to see what has come up, what announcement is there, what quizzes are there, and other assignments. So after now, I will also unhide the next topic, which is angle measurement, so that those who prefer to read before the class can utilize that. And when you go to every topic, I have not given references now, but you realize that under preparatory research, there is a list of references that you can actually benefit from. And one of them is Surveying, is a textbook by Uren and Price called Surveying for Engineers. And I even put for you a link where you can download it. There's another one called Surveying Principles and Applications. There's a lot I have posted onto Mwere. And of course, this is university, it's a choice. You may decide to benefit from it. You may decide not to. But at the end of the day, when we assess, we assume that you have done your part. So I urge everybody to enroll. The course has already started. We shall be having classes every Monday at 8, unless we agree otherwise. And the rest of what you are supposed to do shall be posted onto the platform. So that is it from me. If there's any clarification to make, any questions to ask, we can take them now, and we close the class. So if everything is okay, kindly go to Mwele, enroll, and already start serious business, online business. Sonia has my email, so communication can be channeled through her. She also has my contact. So feel free to channel any communication through Sonia and I think Raymond Molindwa, the class representatives. Thank you. It was nice having you in class. Online, we can interact anytime. For Zoom class again, shall be on Monday at 8 a.m. Or if we have any changes, then the class representatives shall communicate. Thank you so much, and you can already leave. After 2 or 3 minutes, I will then close the meeting.